Hello and welcome to episode 4. Quick recap, where have we been? In the first episode, we used the OHM editor to create a grammar for the programming language Kot, a sort of subset of Kotlin with 6 different kinds of statements, functions with parameters, array types, and identifier types, unary operators, ternary operators, binary operators, a rich set of arithmetic and logic operators, function calls, numbers, string literals, and variables, which could be part of an array, and a handful of keywords. In the second episode, we set up a project. So at the top level of our project, we have a README, have a license, we have a gitignore because this is a Git project, and a package.json where we added C8 and Mocha for testing and GraphStringify and OHM for the actual compiler itself. We've used OHM so far, but we haven't looked at GraphStringify yet, and a prettier RC to not use semicolons. In the source folder, we have a file called kot.js to launch our programs from the command line. We have a compiler, which is eventually going to do more than just parsing, but right now only the parser is implemented. Later, we're going to do analysis and optimization and code generation. And the parser just launches OHM. It reads in our grammar that we created, and it takes in some source code, and it tries to match it. And if successful, it returns the match. If not successful, it throws an error. And that's where we left off in episode 3. Right after we finished episode 3, I did remember to actually commit the work that we did and push to GitHub, the stuff we did at the end. And so I made a commit and committed everything in a commit message called the parser. So next up right now for episode 4, we're going to begin the process of semantic analysis. And that begins with crafting a program representation. So there's 2 parts of the analysis phase. One is to build the internal representation. The second would be to do all of the type checking and things like that. So it's going to be 2 videos. Right now, we need to build a program representation from the match object. The parser gives us a match object. Our job next is to analyze it, and that's going to require building a program representation and so on. So far, what we have in our compiler itself is that we can compile a program from a file which says to compile with a given output type. That output type right now we have parsed. I think we would like to say, what if it was analyzed? So else if output type, I don't want it AST, I want analyzed. If it's analyzed, we'll return analyze of parse of the source code. That's what we're going to do. And then over here, we can say not yet implemented. Can't do anything else yet. Yeah, there we go. And so what we need to do is write an analyzer. So in analyze, let's add export default function analyze, and analyze is going to take in a match object. It's going to return whatever it needs to do. And let's make sure that in our compiler, we can import analyze from analyzer. Good. All right. So what do we have to do with the analyzer? Well, the first step in the analyzer is to build a program representation, build a program representation, and then check it. So type checking and other semantic checks. So things like, are the variables you're using, have been declared or not? Have you redeclared a variable? Are you calling a function with the right number of arguments? That kind of stuff. So we have this idea of a program representation. So what actually is a program representation? Running through the grammar, you can see that a representation of a Kot program is going to be, at the top level, a list of statements of one of 6 different kinds, but each kind has components, right? While statements have a test expression and a body. A variable declaration has a variable and its initializing expression. An assignment has a variable, which is its target, and it's being assigned to source. A print statement has some sort of an argument. Array types have a base type. Ternary expressions have tests, consequence, and alternates. Or and other sort of binary expressions have a left and a right. We have, for the negation, we have a unary expression with a unary operator and a operand. For calls, we have a callee and we have arguments. So these are the sort of things that we need to represent. So it's common to create a file for that program representation, which is usually called core. And what I like to do in core is start building up a number of helper functions for different things. Okay, let me drop the first one right here. We have programs in COT, which are lists of statements. So let's make a little function called program, which when given statements, will return an object representing a node in the representation for a program. For variable declarations, we want a variable and an initializer. But what does a variable look like? Variables in COT will just have a name and a type. So COT supports integers, strings, booleans. Actually, it supports just numbers, floating point numbers, and so on. Floating point numbers, integers. We even have arrays. The next thing we should have, looking through the grammar, we have here function declarations. So let's see if we can capture function declarations. So just like a variable declaration associates a variable with an initializer, a function declaration is going to associate a function object with a body. And function objects, what do those look like? A function object has a name and then it has some parameters. Later when we're going to build the representation now, but later when we do type checking, we're going to see that it will collect a type to go along with it. Okay, actually we have the variables type right here too. So let's, yeah, we can go ahead and just capture let's just capture the return type right here. That's fine. And then after functions, we should have, oh, speaking of types, what are the types? What kind of types do we have? Well, we have some basic types, Boolean, integers, floats, strings. I mean, we could add a void type, but we don't need void types here. All functions in COT actually return something. But if your language had void functions, you'd probably make a void type. That's fine too. There should also be an array type as well, right? So let's see if we can make export function. See if we have an array type. And that should be an array type with a base underneath it. So I think I'd rather call this the base type. Thanks, Copilot, but I would rather say what the base type is. And okay, so we have our function declarations. Function types, no, not in this language. Good suggestion, Copilot, but this is we're not quite this fancy yet. I think we're ready right now to start working on our other statements. So here, let's get the first three statements in here, little helper functions for these. We'll have an assignment statement, which assigns a source to a target. A break statement doesn't have any additional attributes. So, I mean, we could make it a function of no arguments, or we can just make it a constant, whatever. And then here we have a while statement with a test and a body. I think the print statement is probably pretty easy to do. Let's think about the print statement. It's going to look like that. And now let's do our three kinds of, well, our complex expressions. Our complex expressions comes in three forms. We have our conditional expression with the test, consequent, and alternate. And then it's going to have the final return type over here. Binary functions have an op left and a right. I think right now we're tracking types. So yeah, let's just go ahead and track the overall type of the expression. That's fine. And we might as well do that for our unary operands too, although in this case, there's only one unary operator in COT, which is negation. But just in case, we want to do more, we can. All right, so now what about the simpler kind of expressions? Well, there's definitely a call expression. That's a call. And yeah, let's go ahead and let's track types. Let's track the type of the call. And I think we have one more. We have that expression that looks like A of I times J, right? This one right here, which is a plus K. Yeah, this kind of expression right here, this we'll just call a subscript expression. Let's see what Copilot likes for function subscript expression. It has an array part, an index part, and a type part. I like that. That's pretty good. You know, the type actually, really don't need to pass in a type. If we know the type of the array, we'll know the actual return type, won't we? That's going to be the array's type base type. That's actually what it's going to be. So we don't even need to pass that in. That can be nice. And anyway, now we have some helper functions to build the program representation. But what we need to do with these things here is we need to wire them in to our actual analyzer. So the analyzer is going to take in a match object, and from it, we need to create, we need to walk the match, walk the concrete syntax tree. And as we see all of the different pieces of the grammar, as we see the program and we see statements and we see the expression of a while loop, as we see each one of these things show up in the syntax tree, we need to emit the corresponding chunk of the program representation. So that's kind of the idea. And fortunately, Ohm actually makes this a rather pleasant thing to do. The trick is that you have to know a little bit of Ohm, but hence this video. The basic idea here is that given any match object, so given a match object, we can look at its matcher property, and in there is where we can find the grammar. On a grammar, you can invoke create semantics on it. And to a semantics object, you can add in the operation that you want to perform on the match. And in this case, I would like to just I would like to build an operation, which I'm going to call rep. And then what you do is you give this an action dictionary, which you assign to the rep. Okay. And what an action dictionary is it is an object that has with it methods for every single important grammar rule. Like, let's look at our grammar. The first one we have is program, which takes in a list of statements. So in our action dictionary, we say program, which takes in a list of statements. And with that list of statements, we're actually going to do something at some point. Okay, let's say this. Now, we need to actually take this semantics object. We have to do something with it. So before we get too far ahead and add all of our semantic operations, let's see where we're going here. I'm going to save this thing over here, and I'll call this the, so I don't know, it's a representation generator or something, or maybe I'll get lazy and call it an analyzer. I'll get lazy, I'll call it an analyzer because I don't know what to call it. I should get VS Code, try to find a good name for us. Here, it's the analyzer. And then once I have an analyzer, we can pass the analyzer the match object and then invoke this rep operation that we're building over here. And that's going to return whatever we end up returning from program right here. Okay, so that's the overall structure. Let's take a look at how we're going to go through that. So we go through our dictionary, we go through our grammar right here. We see program. And now we see under statement, we actually have various forms of this statement. They all have these case labels. So that means that the corresponding entry in the action dictionary has to look something like this. Statement underscore, I think I wrote it as var_dec. And Copilot's filling out the thing. It says, your variable declaration appears to have, it doesn't have var, it has the word let. And then there's an ID. And I believe it looks like, we should do, let's see if I can split this. Let me split that to the right. There's our own. I'm gonna have to make this smaller. Hopefully it shows up okay on the video. Yeah, so statement var_dec, has let ID =expression semicolon. let ID equal sign expression and semicolon. And that's, I'll just make it look like expression because that looks easier. It fits a little bit better like this. Okay, next up will be our function declaration. So STM2, oops, I think it had it. Yeah, statement fundec, let's see. Function keyword, identifier, left parenthesis, parameters, right parenthesis, colon. No, there's no colon in a type. Copilot is thinking ahead to other languages where you'd have to specify the return type. And then we have, no, we actually have over here an equal sign. And then we have an expression, and then we have a semicolon. Those are the things we have for the function declaration. Next up is statement underscore while, which has while expression block. It doesn't have a left parenthesis. And it doesn't have a right parenthesis. It's just pretty much straight up while some expression and some block. That's what we're seeing here. Next up is break. So statement break has a break and a semicolon. Statement assign is next with ID. It's not an ID, it's actually a variable. Variable equal sign expression semicolon. And then we have statement print. The print keyword and expression. Oh, this one actually does have parens. Left paren and right paren. Okay. Next we have params. And params is just a, how does params go? It's just, oh, it's a list of parameters. So let's just do this for now. Next we have param. That's ID colon type, that's correct. We have two kinds of type. We have type array, and this is going to be the base type, and then the left bracket and the right bracket. So base type, left bracket, right bracket. And let's see, a type ID. Yeah, let's do this. Let's actually try to capture the ID here. So we'll have one for type ID, which will have the ID. Now we have a block, which is going to be left curly brace statements, right curly brace. That's good. Expression, right here, there's a negation part and a conditional part. See here how we have negate and conditional. And then we have one where it just drops down to the next one. We don't have to write a rule for that because OMO passed that through for us. So we just have to take the complex ones. That would be good enough. So expression negate has the minus sign and the operand. Then we have expression conditional, test consequent, test, yeah, we have the test, we have a question mark, we have the consequent, we have a colon and the alternate. Now we have, next one is exp1 with an or. We have the left, the or symbol, and the right. Expression 2 with an and. Expression 3 with a compare. Not EQ, it's this one's actually compare. And this has an operator in here. Expression 4 underscore add, that's correct. Expression, the next is called the term. So term multiply. We're right here. Term is term multiply with left operator and right. That's good. Next is factor exp. Factor exp. Left star, no, not even close, Copilot. Left operator and a right. By the way, We're going to have to keep track of what these operators are. And now we have different primaries. We have primary with parens. Primary parens. Okay, it's just that. We have vars. Oops, let's look at var now. I'm going to put this ID over here because there's two kinds of IDs. Sorry, two kinds of variables. We have variable subscript and variable ID. So var subscript. This has a primary. Oh, it's got an array and then bracket, index, bracket. That's good. And then var ID. Just an ID. Next is a call. Has the callee. Callee is going to be some sort of var, and then left parenthesis args. And not much we have to really capture down here. We probably should, let's see. Don't need to capture that. We'll pick all these up later. We'll pick up our strings. Actually, yeah, we will need to pick up, I think a couple of these things are probably worth picking up. If we ever see the true, yeah, so the true actually takes in some code, but it turns out we're just going to return the whatever we see. So true actually takes in the characters TRUE, right? So yeah, so this is we'll just use an underscore for this. And we can say over here that we're just going to return the Boolean value true. That's going to be the processing for it. And then for false, we'll return false. If we ever see a number, we'll take in, what does the number take in? Oh my gosh, one, it takes in digits. The first part of the number, the int part of the number, and then the dot, and then the fractional part of the number. And then optionally, there's the e part of the number, and there's the exponent sign part of the number, and then there's the exponent part of the number. But when all that's said and done, all this is going to turn out to be this dot source string. It's like whatever text is passed in here, and then we're going to turn this into a number. And I think we don't have to do much more. I guess for strings are going to have the open quote, the characters, and the close quote. And what we'll do is we'll take the source string made up by the chars. And yeah, I think this is actually good here. So this is a good start to building up the program representation. Now we just have to fill it in. And the way all these things are filled in is you say to yourself, okay, whenever I see in the grammar a program hitting some statements, what do I do? Whenever I see a break, like, what do I do? Now, some of these things are going to be pretty easy to do because in our core, we actually had break statement is actually there. So if we see the word break in the syntax, we're going to return a semantic object for a break statement. If we see an assignment, what we're going to do here is the following. We're going to call our little helper assign from core. And you remember that assignment, if we look over here, our little helper function said that in our assignment, we take in a target and a source. Where do those come from? So the target is going to be this variable, and the source is going to be the exp. But we have to descend through this tree in the following sense. When we do the assignment, we're going to take the variable and we're going to recursively call this operation rep that we're using here. And then we're going to do the same thing for expression. So what you do is you walk through each of the syntax pieces here, generating a fragment of program representation. For print, it's going to be a matter of creating a print statement with the exp rep. I'm trying to do the easy ones first. For exp negate, we'll return a unary expression with a negation. Again, unary is this one right here. And similarly for some of the other ones, always recursively doing rep. So test rep, consequent rep, alternate rep. And most of these I think should be pretty good. We're taking these. Yep, that all looks good. Let's look at comparison now. This op over here for comparison is one of the relational operators. Let's see if it gets it right. Yeah, Copilot got it right. When you have op, that's going to be part of the syntax, but we want to store the string, not the node. This is a concrete syntax tree node or a match node. It's a complicated thing. We're just interested in the string right here. So Copilot is going to fill in a lot of this stuff for us. That's a binary. All these are going to be binary expressions. And this one too is going to be a binary expression. Of course, when you have a parenthesized expression, the parentheses are only meaningful in the syntax. They're absolutely not meaningful when we build a program representation. We can completely get rid of them. Here we're going to build a subscript expression with the array and the index. For the ID, if we ever see an ID, this is going to be something we're going to have to work on later. So I'm going to put a note saying, this one is hard. Okay, and for right now, we should return, how about for now, just return the ID as a string. So we'll return the source string. It's pretty good. For the callee, we're going to return a call with the callee rep and then the args rep. I should probably point out something about args rep. This isn't actually what we want. And the reason is the following. Let's look at what args are. In the grammar, args are pieces of the call. This says list of expression. So list of is a very complicated thing in Ohm. It's kind of like we said exp, and then there's a little starred area with a comma, another exp. But what we need to do is kind of turn this into a node in Ohm that has a kind of like a sequence of expressions. We have to actually write things like this, where I got lost for a second. We have to say, okay, args as iteration. Okay, and then once we do args as iteration, now we got a regular node and we can look at all of the children of that. And then we're going to map over it with each expression. We're going to produce exp.rep on it. So every time you have one of these list ofs have to be handled kind of like this. Okay, you have to do with the as iteration. Now, you don't actually have to do that with the program statements, because what you can do here is you can say, all right, I want to make a program, and it's not statements.rep, but it's statements.children, and then we map over each statement in here, and we gather up the representation. So this is how we build it this way. For the variable declaration, variable declarations, that's going to take a little bit of effort, I suppose, because variable declarations are what we have in the syntax. But when we build a program representation, a variable declaration has to refer to an actual variable. So we want to give that a little bit of thought, how that's done. So we need to build both a variable and a variable declaration here. So I'll try to go through that somewhat quickly. Let's do the, let's make a variable object, and it's a variable with the ID source string. And then what are we going to do for the type? What do we need? We need a name and a type. So we have the name, but how are we going to get the type, right? Well, let's see. In a typical a typical COT world, you might have something like let x equal, I don't know, 5 times 2.3 or 5 times 2.5 divided by, I don't know. So yeah, something like this. So we have to actually analyze the expression first, figure out its type, and then whatever that type is, we're going to give to the variables type. So what we're going to actually say here is, let's get our initializer and let's take the expression representation there. Then the type that we're going to have will be the initializer's type. This all requires that we figure out how to create these types. And while we're not actually generating types right now, we're just building a little bit of representation. We can leave that out for a second. So I'll just leave that one out. For the function declaration, we have to do a similar thing. Oh, let's pick up some low-hanging fruit first. A while statement. There we go. That one wasn't too bad. For type IDs, okay. Also hard. Or now just return the ID. Copilot knew what I did below, which was kind of nice. For an array type, we're going to return a new array type with the representation of the base type. I like that. Parameters, not colons, parameters are going to be just variables. So return a variable with the ID source string and then whatever the type is. For params, we actually have to work our way through the list of parameters. And that, again, if you look at the way that the params are structured in the grammar, params look like, where are they? Just a list of. So we're going to say parameters. Oh, let's just say params as iteration and then get the representation, get the actual parameter here. That's good. And then let's see, function declarations also, of course, pretty hard. Let's see what it's telling us or suggesting for us. First, we'll do the bot. This actually isn't going to be right because we can't have recursive functions until, well, a little later. So recursion is hard. Let's defer it a little. But the basic idea is going to be, we're going to try to build our function. We build the function object first. What's the function look like again? It has a name and a parameters and some type. Then we have to embed that function into our function declaration. Going to take a little bit of work there, but it's going to be something like this. Build the function with the name and the parameters. What's it saying about the body type over here? I just need name parameters. Yeah, we don't really have the type yet, but we have to kind of do this in two steps. That's why we're deferring a little bit, because we can't process the entire expression and get its type first, because that expression might need to rely on the fact that that function's already been decided. But eventually, we can get this working. So this is actually a little bit close for now, but what we don't have right now is any sort of test built around it. But this video is getting a little bit long. So what I'm going to do is stop here and say this is just the part where we're sort of designing the program's internal representation, think about analysis. In the next video, I'm going to put together some unit tests and see if any of this stuff is right. I mean, none of this stuff, I haven't tested any of this stuff right. I have no idea if any of it even works, but it was kind of fun to put together and it kind of shows you what's going on with them. Okay, next video, we're going to write tests and see how badly I screwed up. Hope that was useful.